let's talk about inverse functions. Okay, suppose I got a function and you got some numbers, and I come along and I apply my function to your numbers. So in this case, that means I take your numbers and I add 3 to them. So I take 1 and I get 4. Take -7, I get -4. Take 3, I get 6. Take 15, I get 18, and so on. So your numbers aren't there anymore because I did my function on them, and now I've got these new numbers. And you don't like what I did to your numbers. You want them back the way they were. So how can you undo what this function did to your numbers? What function can you use on these new numbers to get them back the way they were? How can you get from 4 back to whatever we started with? You can subtract 3. So to undo my function, f of x equals x plus 3, you can do the function where you take the number and you get that number minus 3. Go from 4 back to 1. Go from -4 back to -7. Go from 6 back to 3. So yeah, that gives us back the numbers that we started with. Notice, by the way, that the pairs of numbers here are kind of the same as the pairs of numbers here, but switched around. We've interchanged the first and second numbers, like the x and y coordinates. But this function here that undoes what my function does, the inverse of this function is x minus 3. So if f of x takes a number and gives you that number plus 3, f inverse of x takes a number and gives you that number minus 3. How about another example? This time I've got a different function to use on your numbers. This function takes a number and multiplies it by 10, gives you back 10 times that number. And if you don't like what this function did to your numbers, what can you do to undo what this function did and get back to the numbers we started with? How can we get from 10 or -70 or 30 or whatever back to the numbers we started with? What function can you apply? You can apply the function that divides a number by 10. Takes x and gives you x divided by 10. That would take you from 10 down to 1, from -70 down to -7, from 30 down to 3, and so on. So that does recover the numbers we started with. So if f of x equals 10x, f inverse of x equals x over 10. Now notice the numbers you plug in to f are the domain of f, and the numbers you get out of f are the range of f. Then the function that undoes that and takes you back where you started, well, the numbers you plug into that would come from the range of your original function and take you to the domain of that function. So for the inverse, the domain of the inverse is the same as the range of the original function. And the range of the inverse is the same set of numbers as the domain of the original function. That's going to be sort of important coming up in a later example, so keep that in mind. Now think about the graph of a function and then the graph of the inverse of that function. Remember how we had the same pairs of numbers just in the opposite order? That means that if you start with the graph of some function, and then you take every point on that graph and you interchange the x and y coordinates. What used to be x is now y, and what used to be y is now x. Then you get the graph of the inverse function. So the whole thing gets reflected across this diagonal line y equals x. So if one function had the point 7,4 on it, which would mean that f of 7 equals 4, then the inverse would have the point 4,7 on it, which means that f inverse of 4 equals 7. And just now I'm noticing that this doesn't match the way the picture is labeled. According to the labeling, this is f and this is f inverse, and I got it backwards. Whatever. if one function is the inverse of another, then the other is the inverse of the first one. So it's kind of a mutual relationship. They're inverses of each other. Anyway, remember the example we were looking at earlier? If f of x was x plus 3, that meant f inverse of x is x minus 3. So here we see the graphs of those two functions, and they do have that kind of symmetry to them. If you take one of those and reflect it across this diagonal line y equals x, you get the other one. So one of them has the point 0, 3, the other one has the point 3, 0. One of them has the point 1, 4, the other one has the point 4, 1. And then compare the function 10x with its inverse, the function x divided by 10. Again, start with one, reflect it across the line y equals x, you get the other graph. One graph includes the point 1, 10. The other graph includes the point 10, 1. You get the point 2, 20, and then here's the point 22. Now, what about this function? This is that greatest integer function, the function that takes whatever number you give it and rounds down to the greatest integer that's less than or equal to that number. So if I plug in 3, I get 3. If I plug in 3 point anything, 3.8 or 3.14, it rounds it down to 3. If I plug in negative 4.91, it rounds it down to negative 5. If I plug in negative 2, I get negative 2. If I plug in negative 1.01, it rounds it down to negative 2. If I plug in 8.71, it rounds it down to 8. So you have these numbers, and I came along and applied this function to your numbers, and you don't like what I did to your numbers. You want them back the way they were. How can you undo what I did here? Well, sadly, you can't. Just by looking at what we ended up with here, you can't tell what we started with. What did we start with to end up with 3? Who knows? Could have been 3 itself, could have been 3 point anything. Anything between 3 and 4. So this is a function that doesn't have an inverse. There's no coming back from this function. No way to undo what this did because it's not a one-to-one function. That means that there's more than one x that takes you to the same value of f of x. And because of that, we can't undo the function because we don't know which of the many possibilities we would have started with. What about the squaring function? If I come along and apply that to your numbers, can you undo that? Well, not really. To undo what we did, we can sort of take square roots, but there's two possibilities. There's a positive and a negative square root. So if I ended up with 49 here, I don't know whether I started with positive 7 or negative 7, because either one, if I plug it into the function x squared, I'm going to get 49. I can plug in either 3 or negative 3 and get 9. So if I want to undo that, I don't know whether starting from 9, I should go back to positive 3 or negative 3. Again, this is not a one-to-one function. So I can't undo it. It doesn't have an inverse. I mean, you could sort of say that the inverse is plus or minus square root of x, but that's not really a function because it doesn't give you just one specific value. It gives you more than one possibility. So that's not a function. If you looked at the graph of the function y equals x squared, the squaring function, and then reflected that across the line y equals x, so you're having all the points on the graph change their x and y coordinates, then you get something that's not a function at all because it doesn't pass the vertical line test for being a function. So before we inverted it or reflected it across that diagonal line, it was a function, but it was not a one-to-one function. the way we can tell that it's not a one-to-one function is what's called the horizontal line test. And I'll come back to that in just a minute here. But a function has an inverse if and only if it is a one-to-one function. So if a function's one-to-one, it has an inverse. We can come up with another function that undoes what it does. If it's not one-to-one, it doesn't have an inverse. So what does it mean for a function to be one-to-one? It means each value of the dependent variable, what comes out of the function, corresponds to exactly one value of the independent variable, what goes into the function. Another way to put it is that for a function to be one-to-one, two different inputs correspond to two different outputs. So if you plug two different x's in, you're going to get two different values for y, or f of x, out. One of the functions we were looking at in an earlier section was g of x equals x squared plus 2x plus 10. We saw that g of 0 turned out to be 10. Plug in 0, you get 10. And we saw that g of negative 2 also turned out to be 10. G of negative 2 is 10. So that this is not a one-to-one function. Therefore, it does not have an inverse. We can't undo what this function does. And I already mentioned that the horizontal line test is how you can tell by looking at a graph whether it's the graph of a one-to-one function or not. A function is one-to-one and therefore has an inverse if and only if no horizontal line intersects the graph at more than one point. So if there's any way of drawing a horizontal line that touches the graph at more than one point, that would mean that there's more than one x that goes with the same y, or the same f of x. That means it's not one-to-one, and it does not have an inverse. So let's try this out on some functions. Which ones of these pass the horizontal line test for being one-to-one? What about this one? No, I see that a horizontal line could touch the graph at two different points, so it's not one-to-one. What about a linear function like this one? Any horizontal line you draw is only going to touch the graph at one point, so it is one-to-one. What about this one? Well, I can see ways that a horizontal line could touch the graph at more than one point. Some horizontal lines would only touch it once, but some touch it at three different points, so not one-to-one. What about something like this? Any horizontal line only touches it once. It's maybe a little hard to tell right around here, but really, if you zoom in enough, any horizontal line is really only going to intersect this graph at one point. So that means it is one-to-one. And what about this? Not one-to-one. Horizontal line can touch the graph at a bunch of different points here. Now, what does it mean to be an inverse function? Well, if you got two functions, f and g, for them to be inverses means that f of g of x equals x for every x in the domain of g. So in other words, start with any x that you are allowed to plug into g, plug it into g, take what you get out, plug that into f, and you should be back where you started. And g of f of x equals x for every x in the domain of f. So start with any number that you are allowed to plug into f, plug it into f, take what you get out, plug that into g, and you should get back where you started. If that works for every domain, or every x, every number in the domain, then these two functions are inverses of one another. So if g is the inverse function of f, instead of calling it g, we can call it f inverse. F with a little superscript -1, that's the notation for f inverse. It's not really an exponent, it's the symbol for inverse.